Okay, this week we talk about moisture. Been a lot of that going around lately. Uh, and I wanted to give you an idea of what moisture looks like a little bit from a global scale. This is a map of what we call precipitable water. So if I dumped, nothing changed, no motion to the air, but if I dumped every piece of liquid that was in the air, that is the total precipitable water. That's how much precipitation supposedly you could get with no winds, nothing. However, air moves. We've learned that. So what the moisture is will be moving all over the globe. We know that the hotter, the more warm the air is, the more moisture it can hold. So you would expect the tropics would be where the most moisture is. And then out of the tropics would come these plumes of moisture, maybe atmospheric rivers they may be called, and they're going to bring the moisture up into our latitude or down south somewhere. And you'll notice that the most precipitation in the United States is in the southern part of the United States. That's where we get the highest precipitable waters. This map is precipitable water instantly right now. And what we're looking at, look, we're close to the equator, right along it. You'll see the highest values of precipitable water right around there and just south of there, as the sun is a little bit south of there right now. So that is an area where precipitable waters are very high. Look at Australia, for example. The sun is slowly working its way back, but that is about where the direct sun is overhead right now. And if that's the case, then that is where the highest moisture content could be, because that's the warmest air. So with that, you can see over the oceans there's more, less over the land. Now, I want to look over the Pacific Ocean, and we can see, starting about Indonesia, working northeast towards the southwestern U.S. and the southern U.S., the western coast of the U.S. there, you can see different plumes of moisture shooting up. These are atmospheric rivers that are being pulled up out of the tropics, and where we had a lot of precipitation on the west coast, you can see one is there now. There's another one in the central Pacific that's moving towards there. You can also see one in the Atlantic. Notice starting about Cuba and working up towards Spain and Europe, there's another river of higher precipitable water. These are areas where the moisture is being pulled up out of the tropics into our latitude where it's getting dumped from storms. So it's really neat to look at where all the precipitable water comes from, where all our moisture is arriving from. And sometimes by being able to track that, you can see just how much moisture you're going to get in your area, how much rainfall, how much snowfall. All very important things you want to know. There's been tremendous flooding in the last week across West Virginia. Out in the west coast of the United States, they've had lots of rain and snow. Those are the kind of things that are important for where we live. They keep us safe by knowing that may come. We take precautions. So that is what we're trying to focus on here, and just understanding a little bit about how moisture moves and how it influences our weather. I am not convinced I'm going to see this blue come up, but if we do, yes. This is the current moisture coming across the United States. It is at mid-levels, which makes it about 700 millibars. The greener it is, the more moist the air is, more higher the relative humidity. This is really looking at a water vapor image. So the closer the green over the Atlantic right now, that is a storm that went across my area, brought sleet and snow to northern Virginia, Pennsylvania, parts of Ohio, very heavy rain to West Virginia, causing major significant flooding there, as a matter of fact, in parts. So all of this is moving across the United States. You can see the moisture coming onto the west coast there. Notice down across Mexico and stuff, it's pretty dry at this level. Doesn't mean it's dry at below that level, but at 700 millibars, it's fairly dry. So there's probably not a lot of precipitation occurring. So this is a great image to give you where moisture may be coming from, if it's going to flow into your area or not. Now, I wanted to take you through a forecast of moisture. This is a numerical model. I'm not going to deal with numerics much with you. We're trying to keep that out of this as much as we can. But there's two things on it. The green kind of indicates higher relative humidity, higher moisture coming in. You'll notice a blue and a red solid line. They are omega or vertical motion. In other words, the air is either being lifted up or pulled down. Blue is being sinking air. Red is being air pushed upwards. As air is rising, it's cooling. We've learned that. And that is where most of the precipitation might occur. So the stronger you see some of these areas where it's rising or sinking, the more you're going to have a chance for precipitation. Looking at this, right away I'm noticing in the mountains of West Virginia, notice the winds are coming from west to east today. Air is falling down the mountains on the east side, so we're getting sinking motion there. Not a lot of moisture around, a little bit down across south to south of me, where I did have some rain overnight in southeast Virginia. And there's some moisture starting to pop up out here in the Midwest. So let's just loop this. This is 60 hours. It's going to go an hour at a time. I'm just going to start it. We'll look at it. And notice how we're getting moisture developing down in here. There's more. Notice the winds have shifted to the southwest. They're starting to pull some moisture out of the Gulf of Mexico. And there's a disturbance running by. And notice at this time frame, there's some pretty good vertical motion across. Most of it across West Virginia again. Here's some more coming through again. And then on out. There's reasons for the vertical motion that we're going to learn in the next few chapters. I just wanted you to get a feel for moisture moving and see it how it moves from the west to the east. Pretty zonal flow, pretty quick flow, actually. These are system after system coming through. So, now that we've covered all of this fun stuff like this and looking at it, let's learn just a little bit about what this moisture is and all of that. So I'm going to minimize this image. We'll bring up a PowerPoint and we'll start playing a little bit in here. We're going to learn a little bit. What is humidity, saturation, and at the end of this, we're going to talk about stability. You're going to get confused by that. I'll just be honest. I'll try to explain it. We'll go through it a number of times in the chapters ahead, but it's something you may have a question about. So water is always being cycled on the Earth atmospheric system. Pretty good thing that it is. We need water for lots of things. We need it to drink. We need it for plant growth. All kind of important stuff. And here's that atmospheric rivers I was talking about. Little different perspective on it, but you can see one coming into the northwest coast of North America there, all the way across the Pacific. And I showed you in that reciprocal water map how you can actually pick up the beginnings of these developing over the Pacific. Pacific is an interesting area with all different sets of mountain chains. I was out there a couple years ago and spent some time traveling around. I knew the mountains were there. I knew there was a coastal range. And when you hit up that coastal range, you get some precip. When the wind's hitting it, they're not as high as the Sierra Nevadas, but they're high enough to produce some precipitation. I have family living on that coastal range, just on the north slopes of it. And the other day, they got 10 inches of snow because of the wind coming in off the Pacific, up the mountains, and they got snow. Down in the valleys, there was a little bit of rain, but it wasn't that much. Now, I have another family member that lives in Lake Tahoe. He's been getting inches upon inches of rain. When above his level, it was snowing. They've had tremendous amount of precipitation because the air, that atmospheric river coming in, is being lifted up that much higher mountains. I mean, the coastal range goes up to 5,000 or 6,000 feet. However, the Sierra Nevadas, it goes up to 10,000, 13,000 feet. Big difference. So there is a total amount of water in the atmosphere that is relatively small, and it's almost all confined below 700 millibars. You get some up above that. And here's where they're talking about the amount of water vapor if you dumped it out. If it was distributed equally, it could make about an inch, not a lot of water, about the whole globe. So we want to learn a little bit about where the water is coming from. We showed you how it's over the ocean so much, and down in the tropics where it can condense, evaporated from the ocean, condenses into clouds as it's coming up. So the whole idea of this water cycle is that the water is going to come up out of the oceans, hit these clouds, rain back. Some of it's going to fall back into oceans. Oh yeah, some of it's going to hit the mountain chains. Some of it may move way inland, even into deserts sometimes. And eventually all of that water may come down through the streams and rivers and flow back into the ocean, or it may come seep into the ground, go into groundwater, which eventually works back. Interestingly, all that water that started from the ocean is salty. But when the water evaporates, the salt is left behind so that it actually comes out as water we can drink. If we had all this salty water coming out, we wouldn't drink it. So we can see how this whole process put together works to give us liquid that really is kind of useful. So we know that water is the only gas in the atmosphere that can change state. So it goes from evaporation, where it's being put into the air, changes from a liquid to a gas, if you would. Condensation is where it's just going back into a liquid from that gas. Roots take in water to the plant, and that escapes out the plant's pores, especially when the plants are very active in the summer, spring, and in the seasons like late afternoon. Interestingly, they did a study in Oklahoma. There's a lot of wheat that grows in Oklahoma during the summertime. They harvest the wheat right around July 4th or thereabouts. Before then, they looked at how much moisture was in the atmosphere. It was pretty significant, actually, quite high. Then they looked after they harvested the wheat. That amount of moisture went down significantly. So that plants like that are putting a lot of moisture into the air, which is a good thing because they're sucking it up out of the ground, bringing it up, and they literally help water themselves by doing that. So now sublimation is just ice or snow becoming a vapor going all the way around. And of course we have deposition, which is the same kind of thing. And we have freezing. Got to get that in there somewhere too, because so humidity, all it is describing the amount of water vapor in the air. I showed you how much more was down south compared to up north. So we, as meteorologists, have taken a whole bunch of different terms, all to confuse you, right? Not really. They're very useful for what I'm trying to forecast weather. We have vapor pressure. All that is the amount of water vapor in the atmosphere. That forms a pressure. We said that each one of the gases in the atmosphere has their own unique pressure. Water vapor is no difference. We're going to talk about mixing ratios, specific humidity, and all those terms quickly here. We just talked about vapor pressure, and almost 4% of the atmosphere's lowest kilometer is made up of that water vapor. What's mixing ratio? All right, water vapor has mass. Any substance has mass. Any vapor, any liquid, any solid. So the mass of water vapor is compared to the remaining dry air. In other words, I have 20 grams of something, of water, of an air. 2 grams of that are water vapor. So 2 compared to 18 would be the mixing ratio. Now, if I left the original amount of water in there, it would be 2 to 20, would be a specific humidity. So the only difference between the two is one, I take the water out and measure it. The one, I keep the water in and measure it. So saturated air, you look outside and you have fog, or it's raining really hard. It's just so humid, right? Well, that's when air is getting close to saturation. Fog, maybe the air is completely saturated. It can't hold any more water. So one of the interesting things you're doing as a meteorologist is you're checking to see the difference of how saturated that air is with time. So the other day, when I when the clouds began to arrive at my house, I could watch the humidity go up, gradually trending upwards. And it reached a point where it began to rain. It had gone up so far, and the clouds had come in. Other days, I can watch humidity go down, especially as the air warms, sun comes out, humidity starts sinking because warmer air holds more moisture. So, when we add saturation to each one of those terms, that gives us how close to saturation we are. So, heating water increases that energy of water molecules, so they readily escape the water surface as vapor. So, in other words, the hotter the air is, the more water it can hold. That's all it's saying. The colder the air is, the less water it can hold. And here you can see that. So we're weighing the water vapor as a pressure. Notice that if the temperature is 122 degrees, pretty warm, it can hold 123 millibars of water. However, if the temperature is 0 degrees Celsius or freezing, it can only hold 6 millibars of water. Whoa, that's a huge difference there. So that's why in the summertime it feels so humid and oppressive. There is a whole lot more water vapor in the air. Now, we learned that water vapor is less dense than normal air. So yes, actually, the more water vapor I add to your air, the pressure is going to go down. Strange. Feels worse. It feels like it should be up, but it doesn't. Pressure is going down. So, relative humidity. We're all used to wanting a relative humidity. When I get up in the morning, I'm kind of curious as to what the relative humidity is to know if I'm going to have fog to drive into work or not. If the relative humidity is around 100%, I might have fog. If the relative is around 60%, I'm not. Nothing to worry about. So, and as the day goes on, the relative humidity should go down, right? Temperatures are going up. If I change nothing in the atmosphere about moisture, the relative humidity is going to go down. And here you can see that. Temperature goes up and down at night. Well, can't hold as much moisture. Relative humidity goes up. Here, temperature starts souping upwards. Relative humidity starts plunging. All that happens if no moisture is being brought in or out of your air. We talked a little bit about the Santa Ana wind flowing down into California there a while ago. Think about it. The air temperature, the wind is pretty dry to start with coming off the mountain. But as it sunk down the mountain slope, the air temperature went from probably close to 30 to 40 degrees all the way up to 90 degrees. We saw on that chart that a 90 degrees can hold a tremendous amount more water than 0 degrees. What happens? The relative humidity, while the water maybe hasn't changed in it, the relative humidity is going to go way down. That's why it looks so dry out there in the West. Dew point is a measure of the temperature you need to reach if you wanted to have dew. Nothing changed. The pressure stayed the same. All we're doing is just cooling the air. We're not adding any water to it. So when I look at dew points, and you're plotting them on the surface weather map all the time, I'm making you look at them in a way. I want to know how close dew point is to the actual air temperature. When they're together, 100% relative humidity, maybe going to be foggy, cloudy, yucky. However, the further apart they are, the drier the air is. And for example, out there in California during that event, temperatures were in the 90s and the dew points were in the single digits, around 1 or 2. Think about how relative humidity was down in around 2 or 3% with that. So here you can see how dew points change from winter to summer. Quite a difference. A lot more moisture in the summer to work with, a lot less moisture in the winter. So condensation will occur. So remember, the air is not the same all the way through the atmosphere. So maybe the relative humidity is reaching 100% at 20,000 feet up. Maybe it's reaching 100% at 10,000 feet up, or maybe it's reaching 100% all the way down to ground. That's where the relative humidity is important to know where that is. All right, we're going to get into stability. The reason we're talking about it here is because we learned that as the air rises, it does work. And that means it's using energy, so it's cooling. Great, simple enough. Dry air cools 9.8 degrees Celsius per 1,000 meters. No big deal, right? So it's always going to be colder than where it is. Now, let's bring moisture into it. So you have this air rising up. Look outside at a cumulus cloud. The air has reached saturation because you have a cloud. Now, latent heat is being released. The air is not cooling as fast. All right, so I'm going to say that there's an air temperature profile here. That air temperature profile is because the air has been mixing and all. It's not cooling at 9.8 degrees Celsius. It's probably cooling maybe at only 6 degrees or 7 or 8 degrees Celsius per 1,000 meters. Now, if I am raising an air parcel up, pushing a mass of air, I don't care how big, and it's rising, when it hits 1,000 millibars or whatever, it's cooled 9.8 degrees. The other air has cooled 8 degrees, we'll say. Whoa, I'm at least 1.8 degrees colder with that air parcel than the other air around it. So that air parcel is going to have a tendency to want to sink. If it's colder, it's denser, it's going to want to push back down. So that air is stable. Maybe just the lift of a mountain was pushing the air up. Maybe there was currents of air lifting it. But there's always going to be a force trying to push it down. So at some point, it's going to overcome that and it's going to start sinking back down. Sinking back down, it begins to warm. Once it reaches the same temperature as the surrounding air, it stops. Now let's go to unstable. That air parcel rose. At some point, if there's enough moisture in the air, it's going to condense. Latent heat's released. At that point, that air parcel is only cooling 6 degrees. The surrounding air is cooling at 8 degrees, we said. So, in 1,000 meters up, I am 2 degrees warmer than that surrounding air. Whoa. Now I'm warmer. I'm going to want to keep rising. I want to rise faster, as a matter of fact, like a hot air balloon. So with that, in turn, going up faster, I wind up with the air being unstable. We've now helped the air to move upward even more. More condensation occurs. Clouds are getting taller. Better chance for precipitation. So that is all this is talking about. The conditional instability is because we reach saturation. Absolute instability, if you have a temperature that's cooling faster than 9.8, I don't know how, but maybe in a little tiny layer you could have absolute instability. There are different things that cause the air to rise. We've talked about convection a little bit, maybe form an updraft from that. What about a mid-hill or a mountain range or a front? All of that. Warm fronts are slower sloped. They're going to bring rain into your area eventually. You just get more, maybe some high clouds first because it's ridging up at the high levels where the most of the rising is occurring and gradually coming down. Cold fronts, a little steeper, a little sharper, better, faster lift. Mountains. If the wind's coming into the west side of the mountains, more lift. We talked about it on the atmospheric rivers out in California. And some areas on the downslope side of the mountains where the wind is, dry. Winds can converge. Great example in Florida. I got faked out by it when I first went to Florida State. Winds come from the peninsula on both sides. They come from the Gulf and they come from the Atlantic. When they come together, they're converging. They don't have anywhere to go but up. They can't go into the ground. So they go up, form these thunderstorms. I assumed, what was going on down there? And interestingly, down in the tropics, air tends to move from the east to the west. Very different than up here. So I'd see these big thunderstorms first couple days I got there, and they were to my east. I thought, oh, great, we're not going to get them. About an hour later, I got soaked. I learned. Hope you got something out of all of that. Let me know if you have any questions.